Now what we're going to do is we're going to prove divisibility by induction. So again, we've got our basis step showing the proposition is true for the smallest element of the set. Our inductive set showing that if the proposition is true for n equals k, then the proposition will be true for n equals k plus 1. The method for proving divisibility is inverted from proving identities. Essentially what we've got to do is we've kind of got to factor out whatever it is that we find divisible. What we're going to end up doing is transforming our equations into a form that shows that the equation is then divisible by k. So it's a bit of a different process. And so what we want to do is we want to look at how that process works in order to prove these kind of divisibility proofs. So let's take a look at an example. Show that for any positive integer n, 6 evenly divides 7 to the n minus 1. So we'll start with our basis step. And our basis step is p of 1 because we're looking at positive integers. So if n equals 1, 7 to the 1 minus 1 equals 7 minus 1, which equals 6. And 6 divides 6. Thus, okay, p of 1 is true. Our basis step is now confirmed. Now 2, okay, we're going to let n equal k. And 6 evenly divides 7 to the k minus 1. Right? So that's our assumption. Now we've got to look at 7 to the k plus 1 minus 1. Okay? 7 to the k minus, plus 1 minus 1. And so we're going to say, okay, well, this is then going to equal, and we kind of got an idea that maybe, okay, this is 7 times 7 to the k minus 1. And so now we've got a little bit of a trick, and the trick is this thing right here. We're going to now make this 7 times 7 to the k, and this is going to then be minus 7 plus 6. And the reason why is that we actually need to somehow, we need to get the 7 to the k minus 1 in here. Right? That's one of those things we've got to be able to do. We've got to get that 7 to the k minus 1 in here. And so one of the tricks that we do sometimes with that is we're going to actually separate out this term, the minus 1, into something that has a 7 that we can actually factor out. Okay? Plus, and in this case, luckily, it's plus 6. So this is going to then end up equaling 7 times 7 to the k minus 1 when we factor out the 7 plus 6. Now, this is divisible by 6. This is, excuse me, divisible by 6 as 7 to the k minus 1, or 6 divides 7 to the k minus 1, and 6 divided 6. So basically what you're saying here is you're like, okay, look, I just added up two things that are divisible by 6, and if you add two things that are divisible by 6, their sum is going to be divisible by 6. Okay? Thus, 6 divides 7 to the k plus 1 minus 1. And we're done. All right? Therefore, by induction, 6 divides 7 to the n minus 1 for n greater than or equal to 0. Yay. And we're done. Let's take a look at another example. Prove that for any positive integer n, 4 evenly divides 11 to the n minus 7 to the n. Again, we're looking at positive integers n, so our basis step is going to be for p of 1. So we'll take a look at that. We're going to get 11 to the 1 minus 7 to the 1 is equal to 11 minus 7, which equals 4. 4 divides 4, thus 4 divides 11, or excuse me, yeah. Thus, p of 1 is true. Excuse me. Take a look at number 2. And what we're going to get, we're going to say, okay, well, let's assume, or let, 4 evenly divide 11 to the k minus 7 to the k. So there's our assumption. Then we take 11 to the k plus 1 minus 7 to the k plus 1. Okay? And this is going to then equal, if you kind of think about it, it's going to be, so what I want to do now is I want to say, well, okay, so what I kind of, I need to get some 7s in here. I need to somehow get a 4 in here. I need to basically make this 4 times 11 to the k minus 7 to the k, or 4 times something. And what I'm going to look at here is I'm going to say, okay, well, I know that 11k, all right? We know that 4 divides 11 to the k minus 7 to the k. Thus, there exists an m, or there exists, yeah, we'll use an m such that 4m equals 11 to the k minus 7 to the k. That's our definition for divisibility. Thus, 4m plus 7 to the k is going to equal 11 to the k, which is great because notice that this is what we've got here. 11 to the k plus 1, I can actually pull out my 11 to the k and have my 7 to the k. So this is now going to be then 11 to the k plus 1 minus 7 to the k plus 1 is going to equal 11 times 11 to the k minus 7 to the k plus 1. And that's going to equal, now I can just substitute in for my 11 to the k. That'll be 11 times 4m plus 7 to the k minus 7 to the k plus 1. And now I've got 4 times 11m plus 7 to the k times 11 minus 7 to the k plus 1, which is equal to 4 times 11m plus 7 to the k times 11 minus 7 to the k times 7, which equals 4 times 11m plus 7 to the k times 11 minus 7, which is 4 times 11m plus 4 times 7 to the k, which is 4 times 11m plus 7 to the k. And thus, 11 to the k plus 1 minus 7 to the k plus 1 is divisible by 4. So the idea here as we're working through divisibility proofs, and they're a bit harder, they're a bit more difficult than other proofs that we've looked at, is we essentially need to kind of like tinker with them in a way, kind of think through them, such that we end up being able to factor out a factor of 4, or make an argument about the divisibility of particular elements. Okay? In this case, we used our original assumption that 11k to the minus 7k, the fact that it was divisible by 4, okay, in order to substitute into some of our algebra. And that actually was what allowed us to actually, in fact, prove our statement. So, what we get here is, by induction, 4 divides 11 to the n minus 7 to the n for n greater than or equal to 0. And thus our proof is finished. So again, one of the things that we want to see with our original proof that we did before and this proof here is that we're constantly looking for or trying to work through, okay, trying to find factors that would allow us to factor out whatever we were looking to divide by, like in this case a 4. Okay? Sometimes it's a little easier than other times. This one actually happened to be a bit more technical. Okay, so that finishes up this particular section on proving divisibility.